The question is, could you show us how to find geometric properties for a composite section? Here we will focus on two-dimensional areas. The geometric properties that we are interested in are these two sectional properties, centroid and second moment of inertia. With respect to the two-dimensional Cartesian coordinate system shown in this picture, the coordinates of the centroid are given by these equations. The equations for finding the second moment of inertia about each of these two axes are these. So here are some standard sections and their properties, and there are of course a lot more. You will find them in books, but these should do as far as this course is concerned. So what do I have here? I have the circle, semicircle, quarter circle, rectangle, and triangle. And for each of these shapes, I have the total area, location of the centroid, and the second moment of inertia about each of these two axes, x-axis and the y-axis. So a couple of things I want to point out before I move on to the next slide. If there is a line of symmetry for the section, then the centroid will be on that line of symmetry. If there are two lines of symmetry, then the centroid will be at the intersection of these two lines. So this semicircle and the quarter circle are examples where you have one line of symmetry. For the semicircle, this is the line of symmetry, right? So everything to the left is mirror image of everything to the right of this line right there, right? So the centroid is going to be on that line. And similarly, if I come to this quarter circle, if I draw a line at 45 degrees like this, you can see that is a line of symmetry for this quarter circle, right? And therefore, the centroid is going to be on that line of symmetry. The circle and the rectangle are examples where you have two lines of symmetry. For the circle, this horizontal line and this vertical line are lines of symmetry. And therefore, the centroid is at the intersection of these two lines. And similarly, for the rectangle, the horizontal line and the vertical line are lines of symmetry, and the centroid is at the intersection of these two lines. By the way, for a circle, of course, every diameter is a line of symmetry. So we just need two of them so that we can find the intersection between the two to locate the centroid. So before we talk about the composite sections, let's state what is known as the parallel axis theorem. Supposing, say, we have a cross-section like this, and we know the second moment of inertia of this cross-section about these axes, x prime and y prime, that go through the centroid. But let's say we need to find the second moment of inertias about these axes, x and y. I will see in a second why we need to do something like that. So the parallel axis theorem helps us do this. Say I'm interested in finding Ixx, right? So that will be the second moment of inertia about the x-axis, right? So the parallel axis theorem says all you have to do is you take Ix prime x prime, which is the second moment of inertia about this local axis x prime, and add simply this term, a times y naught squared, where a is the area of this section, y naught is this distance right there. So y naught is the distance between the two axes of interest, right? X and x prime. And there's a similar formula for Iyy. The proof of these relations are fairly straightforward, and here are the details of how to prove this first relation. Firstly, we note these relations. X can be written as x naught plus x prime. Remember, x naught is this distance, right? Distance from this origin to this origin in the x direction. And then you go another x prime and you get x, right? So x equals x naught plus x prime. Similarly, y equals y naught plus y prime. Now if you differentiate the first equation, you get dx equals dx prime, because this is a constant, x naught is a constant. Differential of that is 0. And similarly, dy equals dy prime. And therefore we see that dA, which is dx times dy, equal dx prime times dy prime, which is dA prime. Now we take this first relation and work on it like shown here. Y here is y naught plus y prime, and you square that. So when you square that, you get this, right? So now I'm separating this into three separate integrals. Integral of dA prime over the area of the section is simply the area of the section, right? So this term becomes 8 times y naught squared. Now, since these two axes passes through the centroid of the section, this term is 0. Integral of y prime times dA is 0. And the third term, by definition, is ix prime x prime. So what we have is ixx equals ix prime x prime plus 8 times y naught squared. So we have proven the first relation. You follow the same approach in proving the second relation. So let's write down an equation that we could use to find the sectional properties for composite sections. So what do? Well, we take the composite section and subdivide that into standard sections. Like for example, in this particular example, I'm taking this composite section and subdividing that into 3 sub areas, 1, 2, and 3. C1, C2, and C3 are the centroids of the sub areas. With respect to a global coordinate system xy, these centroids have these coordinates. C1 has x1 and y1, C2 has x2 and y2, C3 has x3 and y3. A1, A2, and A3 are the areas of the sub-areas. Ix1 prime, x1 prime is the second moment of inertia of this sub-area about this axis x1 prime, and so on. Alright, so there are 6 of them here. In other words, we know the second moment of inertias of these sub-areas about these local axes x1 prime, y1 prime, x2 prime, y2 prime, x3 prime, and y3 prime. First, let's see how we find the centroid of this composite section. And here is the equation for finding x bar of the composite section. In this equation, the integral x times dA needs to be performed over the entire area A. You can see the integral can be divided into 3 parts like this. The first part is the integral over the sub-area A1, and the second part is over A2, and the third part is over A3. We know the coordinates of the centroid of the sub-areas, right? C1, C2, and C3, and the equations for finding them are these. x1, for example, is 1 over A1 times integral of x times dA over A1, right? x2 and x3 are similarly defined. So from this first equation, we can see integral of x times dA over A1 is simply x1 multiplied by A1, right? So in place of this, I can write this, x1 times A1. And similarly, the second integral becomes this, and the third integral becomes this. X bar, therefore, is 1 over a sum of xi times ai, where I goes from 1 through the number of sub-areas we have in the composite section. In other words, we can find x bar of the composite section from the knowledge of the centroids and the areas of the sub-areas. And y bar, of course, has a similar structure, and I'll summarize the equations in a little bit. Now let's go ahead and derive an equation for the second moment of inertia of the composite section about a global axis x. This is the equation for Ixx, and we split the integral into 3 parts like shown over here. The first term here is the second moment of inertia of the sub-area 1 about the global axis x. Ixx2 is that of area number 2, and Ix3 is that of area number 3. Generalizing this, we could write this like this. Ixx equals sum of Ixxi, where Ixxi is the second moment of inertia of the sub-area I. Now, using the parallel axis theorem that we have derived in an earlier slide, Ixxi can be written like this. Ixxi equals Ix prime x prime I plus ai times yi squared. Here, Ix prime x prime I is the second moment of inertia of the sub-area I with respect to the local x prime axis. X prime axis passes through the centroid of the sub-area I. AI is the area of the sub-area I. Yi is the y distance to the centroid of the sub-area I from the x-axis. The expression for Iyy is similar. So here's a summary of the equations for a composite section. These are the equations for finding the centroid, and these are the equations for finding the second moment of inertias. And in this example, I kind of implied that I'm adding the three areas in order to get this composite section, right? But in some cases, you may have to subtract certain sub-areas. For example, if I have a hollow cylinder that is being used as a beam in certain structural arrangement, I need to find the second moment of inertia of this hollow cylindrical cross-section, right? And in that case, the area representing the hole needs to be subtracted from the overall area in order to find the properties of the cylinder. Here are a couple of things to keep in mind when you apply these equations for situations like that. In equation 1, you want to use negative signs for the areas which are being subtracted. And you also want to use proper signs for xi's and yi's. In other words, sometimes some sub-areas might end up in the negative side of a certain coordinate axis, and you want to use the proper signs for the coordinates. And equation number 2, you need to subtract the second moment of inertia of the areas which are being subtracted, like holes.